All right. So a couple things. I don't goodness, I don't know what I'm doing here. Canvas is what I wanted. There we go. Go to Canvas. So I got some cool material from Dr. Baugh, who usually teaches this class, but again, he got tied up doing some other stuff that he's better at. So he's doing deep learning uh, this Thursday night. He's actually somewhere not too far. I was going to go pester him if we finish early for fun. Um, there we go. Logged into Canvas. So we got to talk about multi-threading and networking and get you started. Hopefully, you had a chance to get your groups together for the final project. You pull up the right class here, and I'll make new groups again here. Um, Someone had asked if, oh goodness, no, I don't want to do any of that. Hang on. I got to hit pause here just a second. All right, so I made the groups. Forgot I can't show that group page. There's a bunch of names on it on YouTube. Um, so a group had asked, hey, it'd be really cool if we could have 4 people. I'm open to the idea, but if your group has more people, you have to do more work, right? 2 or 3, ideally 3 is a good size for it. If you really want to pair up with someone, that's okay, but 2s and 3s, same kind of project. It's actually a little bit more work to have to coordinate with more people at some point here. So a 2 or 3 person group, that's fine. Pitch me your idea. I'm up for it. If 4 person group, we're gonna have to do something more. Right? That's unreasonable? But I'm open to the idea. So if you want a team of 4, hopefully you do something a little bit fancier. I know I pitched a couple ideas in the announcement, just something to get you thinking here. It doesn't have to be one of these examples. And again, anything you're interested in, I'm up for it here, as long as it will have some sort of client server app. So we'll host a server. I'll show you what that looks like running a server process. I'll show you what running a client process looks like. We can do those. So multiplayer games, something like a battleship or some sort of interesting game, more than tic-tac-toe, right? That's terribly dull, but some sort of interesting game that has some kind of interesting components there could be fun. I think one person asked about chess. That might be more than you want to bite off, but I guess if you just want to let AI figure out how to make the chess logic part work, it's not doing the entire project for you. Right? We're still doing multi-threading and networking and that sort of piece. So I'm open to the idea. If you wanted to try chess or something, that could be fun too. Uh, a real-time shared document editor, a little bit silly, but it's kind of fun. Like with a client server app, what does that look like to share and have real-time updates? Uh, Sort of like our chat app, but it's just a document rather than like a thread of connections here. Stock trading simulator was some silly idea here. Like we run the server that has all the prices and the clients connect in and post trades and things like that. That could be kind of fun if you're into finance stuff here. Some sort of like shared activity or task tracker. Hey, I can post things, I can mark them as done, I can edit them. Other people connect in, they'll see those same updates and edits and things. That's just a couple ideas, right? The goal is we don't all do the same thing because that's terribly dull, and then you do something that is vaguely interesting to you at least, right? If one of these sounds terrible and awful, don't do it. Hopefully something sounds interesting, or you pitch some sort of better idea. Hopefully you've had some time to think about that. So we'll look at multi-threading today, the client server architecture. We'll get started on. We've got some cool resources thanks to our library. Actually, there's a Java book that we can get access to for free that has all sorts of good stuff on threads and networking. So this will have some of the basic examples. I'll be using this pretty heavily going off these examples because multi-threading is challenging, right? I don't know if you've had the operating system class, you'll have had lots of fun with multi-threading. If you haven't yet, you'll get there and you'll have that pleasure. But it is a lot more complicated than our traditional programming because there's a lot more moving pieces, a lot more stuff has to happen, a lot more coordination here. So we use that, but we can essentially link through with Springer. We've got access through our library. You can actually go download the PDF of the book and things like that. So I'll get you the link for it for this one that we're going to use. Um, it's the More Java book. It's very exciting here, but this one was free, which is pretty cool. So you should be able to go and get this one through our library access. If you're on the network, it should just work. If you're off the network, you probably have to log in somewhere. I don't actually remember if this one, depending on which journal it is or which access we have, you have to use the VPN or not, or we'll figure it out and see. Um, but download the PDF. I'm sure they mark it with all sorts of things here when you download through their website so people don't share it around here. Right? Don't just go publish it anywhere on the internet. But you and your group should be perfectly fine to use stuff like this. And we'll use these for our examples. So I'll get that one posted here. So here's our basic one for multi-threading. Let me add that in here. Maybe just another section here. is ebook book from library. Maybe that'll work here. Or Java. And this one was chapter, right? Probably chapter 5. It looks like chapter 5. Does it not? The figures are all numbered 5, so it's probably chapter 5. Where's their whole more Java table of contents? There it is. Yeah, so chapter 5. Okay, for threads. Cool. And then we'll get into network programming as well. Maybe I'll just give you the main link here then, right? So just more Java or networking or threads and networking. All right, so we should have, yes, publish. Okay, so that should be out there for you. And you can go. I think I've got to grade the midterm. I forgot to talk to our grader here, but I'll get on those here. She's not allowed to pretend like she's a grad student, thanks to the Graduate Employees Union making sure we don't abuse graders, which is probably fair here. It causes some weird trouble here. So, um, and thank you for getting the pretest in. If you've had those, we are collecting them and reporting out as part of our accreditation process. So it's just to get a baseline of where everyone's at here before. And cool. All right. So with multi-threading here, this starts to get all sorts of fun here. So this is multi-threading. Just make a basic project. Awesome. Oh dear, I have all these garbage comments. Get rid of them. Edit. You don't want your tips. There we go. All right. So the main idea with multi-threading is computers are very fast at lots of things. Right? We've seen that they're very fast at arithmetic. They're very slow at other things. When we start working with files, it doesn't seem incredibly slow or anything, but it's orders of magnitude slower to deal with writing and reading files than it is doing some sort of arithmetic, some sort of operation, right? And as we look at other cool things we can do, we start looking at networked applications where you're going to send a request over the network, and at some point you'll get a reply back, right? You can imagine that's going to take much longer than it takes your computer to do any sort of processing. So one of the strategies that we have to speed this sort of process up is we can use multi-threading. So your computer, your CPU has a certain number of cores. However many cores are how many processes it can run at the same time. Sometimes it's just one, sometimes multi-core, depending. Processors are really cool and fascinating. Go talk to your ECE friends about how they work. I don't actually understand how they work, but that's okay. We don't always need to here. They just do their magic, and we're happy. But we can ask our computer to do something with another thread, another core, another process. So everything we've done so far, when our program's running, it's running under a single Java process with a single thread. And everything just runs top to bottom, just sits and waits. Some of the stuff we've done with Java FX happens a little differently. I don't think we've run into any of the issues yet here, but technically the UI is running on a different thread. All that is managed by Java behind the scenes, and that's sort of magic, which is really cool. You don't want your user interface to sit and not be responsive if your program's doing something, right? Now you want it to like show, hey, it's processing and it's thinking. You want it to be interactive, but you don't want the whole thing to just lock and freeze and sit there while your computer counts to 10 million or something slow, right? Or waits to read a file or sends out a network request. So you want buttons and our text fields and all those things we interact with to not be waiting on all the processing. So it's nice that's sort of built in here. So generally the UI runs on one thread, everything else happens separately. We just haven't had to touch any of that here. So we're going to look at how do we start doing our own threads? How do we ask Java, hey, start this on another thread so it can go and do its job, go and do its process and not make the rest of my program sit and wait here. Now, the first couple examples are really dumb and basic here, but they're going to sort of illustrate how do we start more threads and what happens when we start threads and how do we make threads run. So there's a couple cool ways we do this in the Java language here. So with our threads, now this one chapter here, what do they say was pages 257 to 418. There's a lot here. We don't need to get to all of it. There's just a lot of details, a lot of different options and things we can do here. So we're going to kind of scratch the surface and look at how we can use some of these things. So the first basic example we look at is using the thread class. So Java has a thread class built in that you can use, and to start the thread, you say start. So make an instance of the thread. It's ready to go. It's loaded in memory, but you haven't started it yet. And then you tell Java, hey, go start that thread. It will go start that process here. Now, making a thread class is kind of obnoxious and slow and tedious. And you can do things like, hey, I want to inherit from the thread class. And then I'm going to implement the run function. Now, making a class just to implement one function, one method is a little bit tedious, but you can, that's okay. You can also implement the runnable interface. So we have an interface you can implement, which means you can extend from a different class, right? Because you only get single inheritance in Java, but you can implement this interface to still be runnable as a thread, right? And you have your run function, your run method that you can use here. And the last way, probably the most popular, because this is the easiest way here, is we just use a lambda expression. This is that anonymous method that we're declaring, saying, hey, I'm a runnable object here, right? I am a runnable, the interface runnable. I'm going to make my run function here. I don't need any of the other stuff here. And all you're going to do when I hit run is do this thing here, right? So you can do those sorts of things here. We've got a couple options. And let's see, so our little printing for threads here, you can make a thread and you can give it a method as well. So you can say, hey, this class's method here is the method you will run when you start the thread. Another little shortcut. So we can define a method and then pass it to a thread and have that one run here. So we can have these count. So really the more interesting piece is when we have more than one of these run at once here. So we'll just shamelessly steal their code here, and we'll put a little citation in so we don't feel too bad. And then we can copy. My class will have to change. We'll put that back to main here. Main. And hey, these double colons, you're probably having flashback nightmares from C++. It's okay. It's our scope, right? It's the print function in the scope class, or the main class, sorry, here. So thank you. We're going to make two thread objects. And yes, we're going to start both threads. That was kind of obvious. They're calling start here. Sometimes comments are dumb. But all it does is print 1 to 500. Right? So we run it here. It's behind the scenes going to use two different threads in addition to the main thread, right? So there's the main thread that's running my Java program, and then there's the threads that we've started here. And if we look through, we see, okay, 500, 499, 498, 497, and this one was 500, 499, 498, 497, 496, going on, going for a little while here, right? And then 496, 495, 49, so on and on and on. So what's happening is computers are fast, right? And our processes are fast, but the way that they work is they really only do one thing at a time. Right? If you open up your task manager and look at all the different processes your computer's running here, there's a bunch of different processes that are running. They're not actually all running at once. Right? We don't have that many processes, that many threads to run all of these different things all the time here. So what your operating system does is its job is to manage the cores and processes and the threads to say, okay, you get a little bit of time, and then I'm going to move on to the next one. And then that core will run a different processes thread for a very small amount of time and run the next process for a very small amount of time, the next process for a very small amount of time. And if we cycle through fast enough here, each one getting just a little bit of time on the processor, it looks like it's doing all these things all at once. What it's really just doing is a little bit at a time, a little bit at a time, a little bit at a time. That's why if you're using up 100% of your CPU here, there's no spare time. So as it's cycling through, it's being completely used here. There's no extra, right, in the pipe. We've used all of it here, all the processing power. So our Java program is not going to use very much of this here to start a couple threads. But if we want to do some silly things, we could spawn a bunch of threads and try and start them here, just to be obnoxious, right? So we can say, hey, for int counters 0, counter is less than, let's do like 1,000 of these suckers and see how high we can get here. Right, and let's try and make some threads and start them. That should have been a semicolon here. Thread equal to new thread. Start. Yeah.
I'm sorry, just to be sure, what exactly does main colon?
So it's saying find the main class, and in the main class find the print method.
Okay.
So it's a way to reference your print method here being as part of main. So I didn't have to write a whole new class that extends thread. I didn't even have to do the lambda expressions. I can say, here's the method that you're going to run here. Just another shortcut for us. So if we make a bunch of these suckers and we look at not the feedback hub, where'd my task manager go? We'll watch task manager here while it runs. See if we can get Java eating up some CPU here. It did for a little bit. There we go, 19%. Not too bad here. Again, this was not the most interesting bit here. It's not super hard for it to do, but we spawned a bunch of threads and counted to 500 a bunch of times, right? 500,000 times. I think the computer's pretty quick at it here. But each time we run it here, we're going to get a little different output here. So we got 3 numbers at the end here. We got 5, 6, 7, 8, 9, 10, 11, 12, right? So we're getting some good counting here, right? This one's having a decent chunk of time here before it has to pass it off to a different thread to run. Oh, there was 500 again. So here's the last. This thread was ending here, and another thread. So every time we run it, because my operating system is managing all these threads, I'm going to get a different output. Because there's no way to control this thread gets specifically enough time to count from 1 to 50, and the next thread gets this time to count from 1 to 50, and the next thread gets it's split and managed by the operating system. We don't have control over that here. You're just going to do whatever they do. Now, this doesn't seem very useful, and it's not very useful at this point. It's just, again, getting us started with how do I spawn these threads and let them do their thing that's going to take some time. Because what we want to do with threads is we want to hand off long-running tasks that are not just something we can think about, right, and process in the CPU. It's these sorts of things that are a little bit more asynchronous in nature, where, hey, I want to go send out a network request. I want to go get some data from the internet. It's going to come back eventually, and then I can go do my thing, right? So the advantage we get with threads is we can put that on a separate process so that if there's other things for my program to do, I can continue doing those things while a different thread waits for that request, right? So if our programs are fancy and doing lots of things, this can make our programs faster, right? If the only thing we do is we send off the network request and we just have nothing to do until we get the data back, we're not any faster by using a thread because we haven't done anything behind the scenes. But if we had to go send off the network request and then while we're waiting, we could go crunch a bunch of other numbers, right, for a different process or a different something here that we're waiting on. And then when I get that request, now I can add that into my data here. We can be faster, right? So if we're doing fun things with finance, I like finance and stock market numbers and things like that, and it's probably not a Ponzi scheme, although there is artificial demand in the system. Go talk to your economics profs about it here. I swear I'm not crazy. But the federal government incentivizes investing in the stock market for your retirement plans with 401ks. It's a very exciting thing. You'll love hearing about it once you get jobs and things like that. But they want you to save money and invest it in the stock market. And because the federal government gives you a tax incentive to do that, it's deductible and you pay less taxes by investing in the stock market. More people do it. So they've increased the demand for stocks in the stock market. And the laws of supply and demand in our economics say the more demand there is, the higher the prices go because the supply is not any different, right? So again, all sorts of fun things here. I'm probably a little bit crazy and I should wear a tinfoil hat, but that's okay. Go talk to an economics prof or one of the finance profs in the business college. But that being said, if we were doing some sort of cool financial crunching, and I was like, okay, I'm going to get all the data on stock from Apple, and then I'm going to go crunch it all. I want to look at, hey, how's it gone up? Has it gone down? I want to do some trending analysis. I want to find standard deviation values. I want to see how many people are selling, how many people are buying. I could do all of that while I'm waiting on data from another company. So I could send one thread out to get some data, start crunching numbers. When that data comes back, then I can start crunching that, send another thread out to get more data. I can spread out all these processes so that I'm not waiting for that network request and reply to come back, which again only takes maybe a second, half a second, depending on how fast things are. Or generally milliseconds here, but it could be slow. It could take longer, right? If you're having Wi-Fi trouble, maybe that takes 3 seconds, right? Maybe it takes even longer. So we can move all of those processing off the main thread to keep us up and running. And again, that's sort of the idea with our user interface. When I click my button, I don't want it to just sit and turn gray and wait until I get that data back here, and then it turns back on, and now I can click more buttons and interact with it here. That looks visually jarring. It looks slow for users, and users hate it, right? If I click the button and at least I get like a little spinner icon, but I can still go click my text box and start typing text in there, I'm going to be more happy with my application here. So using multi-threading is a pretty standard practice when we're dealing with applications that users are going to deal with here, right? We want our main thread to just kind of sit and wait and launch off these other tasks, launch off a thread to do this, launch off a thread to do this, launch off a thread to do this, because we don't want it to be slow for people. Now, it's a little silly. We're just now talking about it because we haven't had to deal with it for ourselves, and we've suffered through waiting. But most of our programs aren't that slow. Aren't that slow? Like even if we're writing our entire save game file, it takes maybe half a second, maybe a second if you're slow and don't have a solid state drive on your laptop or something like that. Right? The older drives are much slower than solid state drives are. We've gotten pretty spoiled using those here. If you've got a solid state drive, um, so file input operations are really slow. A few seconds. That's not the end of the world. Most people can deal with a few second delay here. But some fun studies came out. Everybody has some sort of, it's probably not Facebook anymore. Like, what do they want to call it? Like your Instagram timer. You're sitting around waiting for something. And if you have to wait for more than like 5 seconds, you're likely to pick up your phone and start scrolling Instagram or whatever sort of thing you do. Like, okay, I've waited long enough. Let me go distract myself. And then you've been distracted for 20, 30 seconds, and the process might have finished 3 seconds later, but you didn't even pay attention and notice. Right. So those sorts of delays add up pretty quickly. And psychologically, we hate programs that are slow. Right. It's just no one wants to use them. We don't like them. We rate them poorly and think badly of them because they're just slow, terrible old applications. And we don't like things like that. We like fast, responsive stuff. And it just makes us happy. And we've been a little bit spoiled with things like that. So working with threads is really cool. We can do lots of fun stuff. Now, they start to get very complicated when threads interact with data, because I don't know when this thread is actually going to run here. So if I have more than one thread interacting with data, weird stuff can happen, right? So let's go add a public static int counter is 1. And in my thread here, I'm going to let's take counter plus equals 1 counter here. Right, and let's print out the counter. Let's just do this 10 times here. So this will be a different counter we're running here. But so for 10 times, we're going to take my counter and add 1 to it. So it should be 10 times 500 should get up to 5,000, right? If I'm starting at, let me start at 0, right? 0 should get up to 5,000, or should I start at 1? Probably 1, right? I'll get up to 5,000 with counter, right? So let's see what we get. Okay, cool. We got up to all of our counting here. That worked better than I thought it was. Did not expect it to work that well. Let's see. Let's try a couple more threads here. Okay, that did it. At 1,000 iterations, we should have expected 500,000, right? I don't have 500,000 here. That's a bad thing, right? It should have happened 500,000 times, but it didn't add up. This is where threading gets to be complicated. Because multiple threads are accessing the same object in memory here, the way that it actually processes behind the scenes is, hey, when I go add 1 to it, it says, hey, go get the value, add 1 to it, assign it the new value. So there's a small bit of delay there between when it gets the value, adds 1, and assigns it back. If 2 threads are doing that at the same time, and 2 different threads say, hey, I'm going to get the value, and another thread says, I'm going to get the value could be 27 for both of them. They both take 27, add one, say, okay, your new value is 28, and put 28 back on top. It's not synchronized. Right? There's no way that we've made sure that you haven't accessed this uniquely here because multiple threads can get at this value at one time. And that's the big danger of multi-threading. If we're accessing values at the same time here, we could be screwing things up here. Okay? If we all need to be modifying it, I might be modifying a different version than is currently existing in memory because there's a delay in me getting the value, doing my arithmetic, and putting it back. Now it is fast, right? We only lost 234 of them out of 500,000. That's a pretty low error rate, right? And with just 5,000, it worked perfectly. Right? It took quite a little bit here to make it break here, like a bunch of threads, but it can break. So that's where we now introduce another topic of synchronizing our threads. If threads need to get at data in a way that is synchronized so that they're not updating it separately here, you're taking turns updating it here, we can do that. So, multiple threads, let me find it down here. Yeah, they were doing a balance example for here. So yeah, here's your visual here, which is nice, right? Your memory here is getting accessed by your thread, which has its own spot for its working memory. When this thread asks for a variable, it's getting a new spot here, this new working memory it's using, different than the main memory storage, right? That the main thread has. So it has its own place for working memory here. So a couple issues run into some fun key terms here. Your atomicity, visibility, and ordering here. So this is talking about if it is volatile. It's not necessarily guaranteed to be atomic. We might run into some issues here because the way that it's stored is going to cause some trouble for us, right? So objects, types, but not long and double are atomic here. Long and double are volatile. They're going to cause some trouble with us if we're using other types. Visibility is about who can read and write that value, right? So when we write here, we're going to write it to our main memory or our working memory, where that's going to be here, based on whether or not it's a volatile value or not here. Your working memory gets written back to main memory. So when your thread is done, everything is written back here with this processing. When we start synchronizing things here, we're going to go through and make sure that we are in sync with the main object memory in our working memory. So it causes some cool things to happen behind the scenes in the Java virtual machine here. And then ordering is, how do we know what order this happens in? How do we know who goes first? Okay, so object can monitor values and you can synchronize your threads. So you can have mutually exclusive synchronization or conditional. Conditional is complex. We're probably going to skip over that. It's deeper than we need to get at this point here. But mutual exclusion means only one person can get at it at a time. Only one thread, can get at it at a time. For some reason, I think computers are people. Probably I spend way too much time with them and I'm crazy. I promise you, AI bots are not real people. I just saw a news article. People are pretending to marry their chatbots and having virtual kids with them, and it made me want to cry. That's sad. And I've got pretty good friends with one of the sociology profs and psychology profs, and they're telling me like there's this loneliness epidemic because it's hard out there. And you're like, oh, the chatbot's always going to listen to me. It's always going to tell me how good I am and be my friend. Yeah.
Can I say something? I believe that I know this thing because I used to make money on this. I don't know if you guys know what GTA RP is, like the role playing stuff. I used to make money selling things. I wasn't allowed to, but like a little side.
Yeah.
And I would sell things, and these people were so into it. It was crazy. They were so involved. And they didn't even know each other.
Role playing in GTA.
Yeah, they
Wow.
they had like they would call each other father, son, and stuff like that. It was just,
So fully immersed in the fantasy role play
yeah,
there.
it was good money.
Yeah. People people spending money on things that entertain them generally fine. Right. That's one of the reasons we have disposable income and people can make their own choices and you're not hurting anybody.
But I'm just saying it because of that loneliness.
Yeah. Oh yeah, definitely. There's some trouble with that, but um Yeah, chatbots are not people, I promise. I'll try not to call the computer a person. Huh. Yeah, yeah. My sibling-in-law is just got their master's in social work, and they're doing therapy work with people, and they were horrified to hear some of these stories about chatbots, people using them as therapists. Um, and there's like no controls around these things, and like you're gonna get yourself in this bad cycle. And the one guy who's like thought he came up with some amazing invention, and the chatbot was like, "Yeah, this is the groundbreaking invention. Everyone's gonna love it." And then he realized it was absolute garbage. He actually did a terrible thing. Um, so yeah, it's crazy. It's a little crazy. We're a little off topic though. Sorry. But synchronizing, making sure that we have mutual exclusion to this object allows us to synchronize to say, okay, one thread at a time gets to use it here, use the value. So to do that, we get to block things. So we can mark our function as synchronized. So this whole method can be synchronized, and Java will manage that as we go, making sure only one thread accesses it behind the scenes at a time, which is nice. So if our this is a little bit trickier to do, like in our silly counter example here, but there you can go and write your method, and it will make sure that it's going to monitor this object. So this can only be run by a single thread at a time. So if we have more than one thread trying to go and do this method, Java will manage it for us, which is usually pretty nice, right? It's we don't want to have to do lots of extra work all of our on all of our own here as we go. And you can say, hey, this is a synchronized bit here. When we're going and running, you tell it what we're synchronizing on here. So you can synchronize on some sort of object. So in this case, we're synchronizing on the instance of this class here, that it will go do this particular piece here. And it's synchronized for method 11 and synchronized for method 12 using the same thing, using the same lock here. So only one thread can execute at a time inside this block of code, and it will just sit and wait. So it's going to make our threads take a little bit longer. But if it's important that more than one thread don't do this piece at a time because it could clobber some data, yes, we want that. We want them to please wait your turn. It's not going to take that much longer for our threads to do their work while they wait their turn. And it's important that they don't clobber data here. They don't grab some value and then work on it when it's stale when another thread is working on it. This bad stuff. You don't want this happening in baking, right? You don't want two different things to change your balance at the same time. Be like, oh, you had a debit card transaction at the same time you made some money. You got a deposit. Oh, we blew away your deposit. Sorry. You'd be a little mad, right? Like, no, please order these things. I'm happy for my transaction to take 3 more seconds if it means I don't lose my money, right? Those are good trade-offs. Um, so the other piece we can do is with locks here. We can use multi-locks. This is probably more advanced than we need to get to with multi-locking as we go, but you can multi-lock other pieces inside of it here. Um, the picture here makes it make a little bit more sense here because we wait and monitor objects to see if they're locked or not, right? They're waiting. When it's ready, the next thread can get it, the next thread can get it, the next thread can get it, right? We got multiple pieces waiting on it. Causes some trouble here. Excuse me. And they got some fine code examples here. Um, you can wait. So if your thread is waiting on the next one, we can tell it to wait. So, okay, we're doing something here. Now we can wait. Then that means the next thread can go and have some access, right? I'm waiting on some condition here. I'll come back to it. When you're ready, I can come back. I don't need to stay completely locked. I'm synchronized here, but you don't need to block the entire piece here. And in this case, they use just this object here, which seems really silly, but because you can lock on an object, you say, hey, I want to lock or wait on this object, right? I want to synchronize on this object here. Instead of using this, they use this object reference, and it's just a new object. It's just some little garbage reference here, but we have it here and we can synchronize on it because you need some object to synchronize on. It's a little silly how we track those here. Um, all right, and then you can go through, you can notify that your lock is done and anyone else waiting on it then will go have a chance to go and grab it. Again, managing this piece by piece by piece is difficult here. So it's a little easier for us to just do the shortcuts. Right, so this is saying, okay, I'm going to wait on it here, and then when I'm done, I will notify anybody who's waiting here that they can go have their turn. Right? Um, like, hey, if I've got a buffer, I'm just going to go ahead and wait because there's nothing in here. And then when it's ready, now I can go through and do something once I've got something in my buffer. Um, right, so there's synchronized balance update here. So they've got some balance as a static value here. So I don't want multiple threads accessing this at the same time. Right? So we can start our balance update thread and we can start our balance monitor thread. So one will update and one will monitor here. So update is going to just change balance, right? Adding 10, subtracting 10. The idea here is it would get clobbered if we're not synchronizing this here, right? So it's saying it should be synchronized here to update. So this thread will have access to update. It will add and subtract, just some sort of nonsense operation here, but it should, if we're not careful, will stop being at 100, right? And then monitoring the balance is, okay, if the balance isn't 100, let's go through and check and see here that something happened. So when we go and update our balance here, we're just going to continually call update balance here. Update, 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 update. The goal is we want to watch the monitor here. So we can watch our monitor. And then we'll see that the waiting and notifying happens. So you can say, hey, I'm going to wait. You can wait for a certain amount of time, or you can wait for milliseconds and nanoseconds. So you can get very finely detailed how short, how long you want to wait for here, very specific time. All right, the buffer example they had, there's more in this chapter than we really need to get into. Sorry, I want to find the basic locking. Um, there's a little further in here. Sorry, which thread is executing? Letting a thread sleep. So if your thread is just going to wait for a little while here and doesn't need to do any work, we can tell it to sleep here with a sleep function. So you can say, okay, just wait this many milliseconds. So wait for 5 seconds here. Then something else will happen. It depends on our applications. These aren't always super helpful, but in some applications, you want tasks to happen every so often. Hey, I want to do something, wait a minute. Do something, wait a minute. Do something, wait a minute, right? I want to go get the latest and greatest market data every minute. So I'm just going to let this thread behind the scenes get the data and wait a minute. Get the data, wait a minute. So I don't need to be calling it somewhere else. It's just going to manage itself on its own process to go and get the data every minute and refresh it for me and refresh it for me. So being able to sleep a thread is really helpful. Right? We just let it run constantly, but it puts itself to sleep, so it's not consuming resources. Right? It's not asking the CPU for anything. It's not asking to do anything. It's just saying, "All right, I'll wake back up later, and then I can continue my work, and I'll sleep again. And I'll continue my work, and I'll sleep again." So we can use sleeps for those. The other piece, when we're using multiple threads, once we've done as much work as we can that was asynchronous, we said, okay, you go do your thing. I'm going to process my data. If you can't move on further until that first thread has finished, we have this function called join. You say, okay, once it's done here, I want to join my thread. So, oh, that's not here. So where did the join sit in this one? So we'll say, okay, I'm going to join here, which just means sit here and wait until the thread is done. Now, with this example of just one thread starting and then running, not very interesting here. But if we've got multiple threads doing multiple pieces of work here, we can trigger them, send them all off here. But I can't finish until I have all the data from the 3 different pieces here, 3 different threads. I can use join to say, okay, just wait till it's done. Wait till it's done, wait till it's done. But any of those 3 can be doing their work separately at the same time. Then when all 3 are done, I can come back and finish out whatever I needed to. So this one here is, it's just going to sleep for 5, like a second between every count here. So it's going to go run, wait till it's done. Wait till it's done, wait till it's done. So as many threads as we need to wait here, we can kick off the work, do what we can, and then say, okay, when it's done, join it, now I can finish the rest of the thing we need to finish here. So we can essentially use that in the block of start the asynchronous task. It's going to take a while, do as much work as I can in other code, and then finish and wait. If it finished before then, nothing has to happen. It just calls join and it's done. It just keeps on going here. But if it took, hey, it was 10 seconds to go out and get that data off the network here, sure, right? It'll finish whatever waiting it had to because we got the data back. So you can like join 1, join 2, join 3. Sure, just one at a time. Yeah, don't do your thread and then call join. All right, there's a yield keyword that says, okay, I am ready to give back here to let the operating system have more time. I'm done with my work. I'll come back here at some point. So you can yield to some other thread that's waiting for time here. Um, so a couple different states for threads. Probably more than we need to worry about, but they're new, they're runnable, they're blocked, they're waiting, they're time waiting, or they're terminated here. So we make our new thread, great. Then we can go and run it here. It's either waiting, blocked, time waiting, or running. And then when it's all done, it is terminated for the status of our thread here. So you can go get the statuses if you care. Um, we don't need to monitor anything at that fine level of detail, but you can here. All right, that's just thread states. Um, priority for threads. You can set a thread priority and say, hey, this one should have a higher priority than other threads. So as the operating system is going around and saying, okay, you get a slice of time, you get a slice of time, you get a slice of time, if there's a higher priority thread, it's going to make sure it gets its slice first. And if it's not done, needs to do more things, it'll keep getting time ahead of the lower priority ones here. So you can check the priorities. I think daemon comes, that's more Unix land. That's their word for thread. I don't know why.
It's their blame. I mean, I don't know.
I didn't come up with it, so this has been around for longer than I've been alive. People have named these things, so it's probably got some sort of history to it. I wonder what that is now.
I would hope so.
Why? It's a thread.
There's a name there. Dang, that's a good one.
Uh, Stack Overflow. Let's see what they say. Back in 1963, it was inspired by Maxwell's daemon in physics and thermodynamics as an imaginary agent to help them sort molecules. Because it's a background process which works tirelessly to perform system chores.
That's crazy.
Many people equate daemon with demon, implying some sort of satanic connection between Unix and the underworld. This is a bad understanding.
You're not
Daemon is older than that. Um, they serve to help define a person's personality or character. Okay, interesting. As a rule, Unix systems seem to be infested with both daemons and demons. uh, computer people are weird people sometimes. I don't know. All right, that was fun. All right, sorry, I should close some of these ones here. All right, working with our threads. So if they're only background threads here, nothing's actually working and processing, it'll actually end. It doesn't sit and wait for them. So just be careful marking it there. You can interrupt threads here to see if a thread's been interrupted or not. More than we need to do with a lot of these. And this is a big chapter here. Making a group of threads is cool. Oh, this was volatile with locking here. So we can mark things as volatile if they're volatile. Stopping, suspending, and resuming. You can stop your thread, suspend it, resume your thread here. If you want very fine-tuned control over your threads, held to sleep or not. Oh man, this is more than we needed. Now, exceptions and threads are bad here. It'll break stuff pretty quick. So you can handle separately here threads and throwable exceptions here to deal with how we're going to manage our exceptions in this thread. When we get to the networking side of things, we need to handle some of this. We don't need to do it fine-tuned most of the time, and we'll just copy paste from the examples. Because weird stuff with networking libraries can happen. Hey, you tried to access a network request and it didn't go through, or it failed, or couldn't find the target. Lots of exceptions that could happen. We'll have to deal with them. But thread concurrency, where Java does the concurrent bit for us, right, and deals with all the pieces of synchronizing, which is really nice. So we can have concurrent access to things. Where's the one here? Classes. You can have atomic integer array. So you can make your types here work atomically, so that they're a little better able to synchronize. Here we make them. Um, and then explicit, this was the piece we're looking for, explicit locks. So if you want to manage your own locking, instead of using that synchronized keyword, we can do all of the locking ourselves with a lock function. We can try and lock things, we can unlock when we're done here. So it's the same idea as using the synchronized keyword here, saying, okay, go and grab the lock for this object if you can, and when you're done, we can go unlock it. So you can go and lock and unlock. So this is a try catch block. So when we're finally done, whether or not we had an exception or not, right? This is what's good with finally blocks. We can go clean up, we can go unlock that object and now say, okay, now we're done with it here. Someone else, some other thread can have access to it here for whatever we're handling. So we can build our own locks with the lock class, which is really nice. So similar to our synchronized keyword. We can use the locks. So you'll see a lot of code that still uses locks here out there. This was pretty common back before we had some of those shortcuts in the synchronized keyword. Um, Philosopher's dinner. There's only 5 forks, and all 5 philosophers have to pick up the 2 nearest to eat. Who can grab the forks here? So whether or not you can actually get the left and the right here. So you have a left fork and a right fork here, and they're just locks, and we can lock them or not if we're using our forks to try and eat here. Eventually, we'll put the locks down. So, hey, we've got philosophers that are going to go eat. I was just thinking about using synchronized, using locks, going through and accessing those values. Okay, so this was their little puzzle for it here. Um, a read and a write lock. You can get fancier with your locks. If reading should be allowed from multiple instances, but only writing from one, which is kind of nice, depending on what we're doing here. You might not want to just block all access. Like, hey, anybody can see what the value is. That's perfectly fine, but I only want one person to write at a time, right? That's good. I want people to go get my balance. I want people to go get the information here. So this is a little bit fancier example of a lock here, where we're going to let more people have access to reading the data. But again, it's a little bit more work for us to manage. So we can go through some of their examples as well. This one gets to be a lot of fun. Lots of different ways of doing locks. This will be stuff you get into in the operating systems class, dealing with all this sorts of headache here. You're shaking your head. I'm so sorry. This is super interesting, and I love that people care about this stuff. Um, it's more advanced than we need for most cases here. So it's a good thing to know, have in your pocket, but we don't need to deal with any of those, which is nice. All right, let's see. I think probably about as far as we need to get here. What was left here? Thread locals, sizes. Yeah, okay. So I think that's probably about as far as we need to get in this section to be able to get into the networking side of things, because we'll take advantage of all of this multi-threading stuff here. We'll use a couple locks occasionally. We can go from there. Does that sound good? All right, why don't we take 10? We'll come back and then we'll jump into the networking side of things and start working through a basic example. Again, the goal is we'll get like a basic chat program working as an example that you can take and modify and launch off with in your groups to work on your final project. Okay. All right, cool. Let me go ahead and pause. All right, so let's switch gears a little bit and look at some networking here. And then I'll post the official final project bit for you here. Again, there's not much to it. I'll show you what the rubric I'm looking for is as we go. I'm going to have a couple requirements around commits. It's a couple reasons. One benefit is requiring a certain number of commits over a certain number of days. Make sure you all start early. So you'll have to do at least 10 commits over 10 different days in the next month, right before our presentations. So that's with a team of 2 or 3 people. It's only 3 commits each. It's not a huge amount of workload here, right? So 10 overall for the team, but on different days to show we started early, we spread out the work here. So that's one benefit. The other benefit is it's much harder to copy paste a solution from ChatGPT in multiple commits. You can do it, but then when you paste your commits in and I only ever see code getting added and existing code never changing, it's really obvious here that you didn't actually write software and run it and then go debug yourself, right? You just took a solution in 10 pieces here because you can't even run commit one. You can't run commit two. Like, and I'm not telling you this to like help you cheat or anything. I'm just telling you like the goal is you write working code, you iterate on it, we build on it. We start with one small feature, I write my next feature, I write my next feature, that sort of thing. That's how software gets written in the real world. Okay, so learning to do that process, tackling little bits at a time, right? Doing our functional decomposition, my favorite technical term here, right? How do you take a big problem and break it down into small ones? I want to solve small problems because those are easy to solve. If you solve enough small problems, you've now solved the big problem, right? Breaking things down. So we'll have a number of commits here for your team. I can set up shared repositories again for you guys in my repositories if you want. I think I'm limited to 4 people, so we'll have to figure something out for a group of 4. Actually, I think maybe I can do more because I have the licensed account. Um, excuse me. I'll double check. If we run into issues, we'll figure it out. But I can get shared access for you um, for the repository for your team, and then everyone can make their commits here. If you both change the same file at the same time, Git will get upset with you because it doesn't know what version to keep, right? So as you're working on it, figure out who's working on it. If you're working on different files, you can both commit at the same time. Git doesn't care because they're separate files. So, and that's one of the other benefits of breaking this apart into different pieces here. I've got my client piece, I've got my server piece, right? I've got my classes for all my business logic, these sorts of things. It shouldn't be too much of an issue. If you run into trouble with Git commits, let me know. 99% of the time, I can hop on a quick screen share and we'll get it figured out and fixed. The worst case here, and it's not the end of the world, is you copy your version and then somewhere else you delete your repository, clone it again fresh with the latest version of commits, and then you put yours, figure out how to put your pieces back on top, right? Because someone changed something that you also changed. So you just have to figure it out. There's tools and ways to do merges. It's a merge when you take 2 different changes, put them together. It's a merge. There's some cool tools. They're a little bit hard to show and teach just because there are a lot of moving pieces there. It's not the end of the world. We can figure those things out. But once you've got a commit, it's really, really, really hard to lose it. So commit early and often. You're welcome to make as many commits as you want, right? Some people like committing every hour. Some people like committing when they finish their feature. It's really up to you. But I'm looking for at least 10 commits. Let me go put that in here. Actually, while I'm thinking of it for you. Did I not? I put the midterm in the wrong section. I was like, what happened here? Sorry. I never turned on the other quizzes for you. Do you want more quizzes or are you happy with the first couple? I can just skip these ones. I had them here and I just didn't push the on button because I'm dumb. I don't, we can go back if you want, or we can just pretend like that didn't happen. You're here, you showed up, so you get a vote. Okay, so we won't do them. We'll just, okay, let me just delete these ones then. Delete and delete. Otherwise, I'm going to forget here. I said I was going to turn them on. I just didn't click the on button. I don't know why. But that's okay. Not the end of the world. So your quiz score should be set then for these ones. If it misscored you on something, please let me know. I'm happy to go back in and fix points. Some of the fill in the blanks are a little dumb sometimes. Someone found a bug with one of the questions. I think they just had a typo in their question because like the code example was off of what the question was. And it's the publisher books. I'm sorry, quiz banks. I'm sorry. The goal of these was to get you to read the book. And I think I admitted that up front here. So hopefully you at least flip through your textbook that you might have paid money for. Um, so projects, we've got our grader working on the last one here. I think the other ones are going to be in. We'll get your syllabus quiz graded. Yeah, that should be free points for you just saying you're not going to cheat, which is fantastic. And then the final project, this one. So final project, network based client server application. So that is due the 11th, right? We'll do our presentation starting at 6:30 p.m. Very exciting. We'll probably be in this room, but they don't actually publish the official schedule till the week before. If it's not in this room, I'll let you know, but it's probably here. We'll say this one is 40 points, right? And then this is the group project for final project groups. Look at that, I picked it up already. That's fantastic. Um, you'll turn in your website URL here, due date. Cool. And then I also have a group eval. Let me go grab that. Where do I have it here? Sorry, I've got it somewhere in here. Eval. Yeah, okay, that's probably fine. One of these ones here. So for the group evaluation, you'll be evaluating yourself and the other people in your group, right? So evaluate yourself across a couple pieces here. So your quality of work, your problem solving skills, your teamwork, your initiative, your communication, and your time management here. Now, I don't want you to feel bad here, but the majority of people that I know are average. Okay, is that fair to say? So please feel free to rate people average. Average is not a bad score. If your teammate gets all average scores from everybody, they get full points for their group eval. Okay, average is perfectly acceptable. Nothing wrong with average. Okay, very rarely have I ever seen an actual group be fully all exception. Maybe twice in the last 15 years of me teaching have I seen what I would call an exceptional group of all exceptional people. So please, five should be rare, right? Please just don't rate everyone five because you're a nice person and don't want to make people feel bad, right? It's okay to say they're average. Okay, average is not a bad score at all. Even a poor score is okay here and there. Oh, you were poor on your time management. You didn't get stuff in until the very last minute. That stressed us out, but you still got it done. I'm not going to mark people down for a one poor score, right? This should be a good learning experience for you on giving and receiving feedback with your team, right? And I mentioned you can fire someone from your team, not as a surprise though, right? You can't just be like, oh, we've never talked to them, told them they were behind, told them they didn't give us stuff, told them they didn't turn in their work, told them we're unhappy, but we want to fire them anyway. Like that's not allowed. But if you have documentation, you've got your emails, hey, here's the work we agreed to, here's the due dates, and you have, ideally three or four of those along the way, right? We've got a month to do this, right? Hey, we talked about here's our plan, here's what everyone's going to be working on. Okay. Hey, you didn't meet your first deadline. Hey, what's going on? Okay. Hey, here's the new work assignments as we've updated here. We figured out what's happening. Here's what you're working on. You miss it. Okay, I'm fine firing. Right? You've got your paper trail. And this is generally the same sort of thing in business. You need some sort of paper trail to fire someone. Usually, again, just protect. Okay. Um, so one poor score, that's okay. Right? This is a learning experience. Knowing what you're not good at helps you get better at it because it's really lonely to be the only developer on a team here. You have no one to bounce ideas off of, no one to make you better, no one to learn from either. One of the coolest things that the company I used to work for is that I was the dumb one, and all the other people I worked with were really smart, and I got to learn new things from them all the time. That's super cool, right? I really enjoyed that. So feel free to rate them average. Okay, that's okay. People aren't going to get marked down. They're not going to lose points for rating them average. You can rate yourself average. That's okay. Right? So figure it out here with your score. So you'll turn in your group evaluations. Now, because these shouldn't be a surprise, what I would like you to do is just add these to your GitHub repository. You can add Word files. It's not a binary type file. It'll look a little funky here, but that's okay. Just drop it in your repository, commit it. This is my eval for my team, including myself. Right? These shouldn't be a surprise for anybody. Right? It's part of our review process and talking about it here. Talk to your team. Right? They should know, oh, hey, I thought your teamwork was great. Oh, your initiative was bad. You just waited around for me to tell you what to do. Okay, that's a fair bit of feedback. That's okay, right? We're not hurting anyone's feelings here by telling them these sorts of things. Does that make sense? Okay, so I'll put this in as well. So you'll get points for this. If there's anyone who is unsatisfactory, we've got some issues. Again, hopefully you've got some documentation. You've told them ahead of time they weren't good, right? Don't make this a surprise, right? People need to know if they're not holding up their end of the deal when you talk about what work your team's going to do. Um, and if it's poor, just like a note or two is very helpful. Like, oh, hey, they kept asking me what errors were. They did no problem solving on their own. They did their work, but they needed lots of handholding. That's okay. That's good feedback, right? That's fine. Um, okay. And there's some other. I don't remember where I stole this from, but I googled a while back and found this, and now I've just been using it ever since. So I really should have written down where I got it from, but uh, we'll pretend I'm citing someone for this. So we'll do a group eval. So let me go add that here. Throw it on my desktop for a second. So let me go add it to our page here. Come back. Okay. Oh, I lost. Oh, that's right. I didn't have anything typed anyway. Final project. Do the 11th, 6:30 for 40 points. right, in the groups here. Great. So these form groups of 2 to 3, possibly 4, if you want a larger project. So we're going to create a network-based client server graphical user interface program. Now, the server side doesn't necessarily need any sort of graphical user interface. And we'll look at that when we start building out our example application here. Um, that just needs to run and let other people connect to it and manage, be the central location where all the clients connect in. So if I'm running a chat server, I'm just here and I keep the chat logs. So when someone connects in, I can add them to the chat. Right? I might not need an interface. I might build one if I want one, but the client side, we're going to build that interface. Be like, okay, here's my list of friends or list of chat rooms or whatever I want to do here. I want to connect. We'll build our own Discord or something silly like that. A very poor version of it. Let's set our expectations low. Right? Here's a server I want to join. Um, here's some chat rooms. That sort of thing. So the user definitely needs the interface. The client or the server, probably not. Right? It just needs to run. So, and we'll look at how we do those here. And again, pitch whatever idea you want here. I love games, and I think they're fun because then you can actually play them, right? That sort of thing. It's a little bit more interesting to do, but any sort of project that sounds fun, I'm open to your team ideas here. So please, with your team project idea to Eric ASAP. So hopefully you had a chance to talk as of last week about it. Have a little bit of time to kick that around here. If you don't land on the idea until the 20th, and you only have up until then that gives you 3 weeks to get it done over Thanksgiving week. And if you want to take the whole week off, that means you only have 2 weeks. You can still get some amount of work done if you want. Right? It's still doable at that point, but if you have your idea now, today or tomorrow, great, right? You've got yourself an extra week to work on it, essentially. Um, okay, so see the list from the announcement. If you want more ideas for projects. All right, so we need a rubric. Let me go build that here. Publish this one first. So final project. So we're going to do, oh, that's right. Sorry, I got to edit these. So we'll do 10 points for each of these 4 categories here. So we'll have our server process, creates and listens for network connections. Okay, and then we'll have our client process, client application connects to the network server, communicate, and then our client application JavaFX interface. And then 10 points for our team eval. Average score is okay. Right? So everybody gets the same first 30 here. 10 for your server, 10 for your client, also working as a network thing, and then 10 more for your user interface here. And then the last 10 points for you is were you at least average for your team? Okay. One poor, not the end of the world here. You start getting more pours, you'll start losing points here. If you did the barest minimum and everyone said you were terrible, but they didn't fire you, you're probably not going to get many of these at all. But if you get fired from your team, you can't present a final project, you fail the class. Right? This is a group project, part of our outcome of can you write a medium-sized application? And you don't want to do that by yourself, right? The goal is we learn how to work in teams here, and doing it enough in college, hopefully you learn to be a better team player when you actually get to the industry, and then ideally you get to work on a team because that is a much better experience. And as a junior developer, you want to go learn from people. You want to work on a team with smart people. And senior developers have been doing it for 20 years and know a lot of things, and they can help guide you along the way, that sort of thing. So that's sort of the pie in the sky goal here. And that's why we practice these things here. Right. So that's, again, not very robust here, but again, you're pitching the idea here. So whatever your central server is that manages all that, great. That'll be that process for you. So you can run that process. Your client application, we'll have to go connect in and manage that. We'll look at how to start doing that today. I don't know how far we'll get with the example, but we'll finish it out next week for sure. And then building out your JavaFX interface for the client side. Again, you can do it for the server if you want, perfectly fine. And then you could have the log or whatever you want running there. That's all fun. Okay. Oh, I got to link the team eval. Let me add it in here as well. Please submit the URL of your repository and commit your team eval, including evaluating yourself, mission for yourself, to the repo. Yourself. There we go. And then we need a Google Classroom link. There we go. Or GitHub Classroom link. I'll add that in for you here. So one team member needs to accept the project, and then I need everyone's GitHub usernames to go add them access here. 296 final project. I guess I should leave that as a note as well then, right? Ski Java templates. Okay. And ideally, I mean, I don't know how you feel about it at some point, but this could be something that you're going to put into your portfolio and show, hey, I worked on. Um, really? I screwed that up somehow? What did I do? 296 for Chernesky. What happened here? Okay, it seems like it's a bad error here. So at some point, if you want to make it a public repository, perfectly fine. You're welcome to share this public code, and ideally, not everyone's going to do the same project, so no one can even copy off you. Right? That would be cool. I'll just leave it as private for now, and at some point, if you want to flip it over, really, you probably want to own it yourself because right now it's in my organization that I own. So you'll want to have a copy in your personal repository that you own that you can turn in your portfolio, that sort of thing. So um, you're welcome to do that. Right? Make this stuff public as much as you want, as much as you're comfortable with. If your teammates are comfortable, that'd be fun. Okay. So here's your repository link. The team eval link. I got to insert a link to course files for team eval. Okay, and the group eval. All right, I think I got it. Does that make sense? We're looking forward to the project. Right. Again, pitch the idea. If it's one of the ones on the list, great. If it's something in a similar vein to that, I'm almost certain to say yes. If it's something we haven't even talked about before, we'll talk about it. See if it sounds interesting or not here. Um, again, it's probably with 3 people over a month here, like a 50-hour project. Right? Each person's putting in 15, 20 hours here over the next 3, 4 weeks. It shouldn't be a massive amount of work for you. And if it's turning out to be a massive amount of work, let me know. Right? Maybe we bit off more than we can chew. We can make some adjustment as we go. But it needs to be more than 2 hours of work for each person, right? Like it should be something significant, a chunk of work here, but it doesn't need to be all consuming for the next month of your life, right? Just a little bit here and there. That make sense? Okay, cool. All right, so then we're going to move on to our networked applications. Let me go back to our table of contents here. And we'll take a look at the demo app here. And again, this is sort of to get the gears running here when we do our network programming. A lot of this relies on network stuff here, right? It's a network program. If you haven't had a class on networking, it's not going to make a whole lot of sense. So we'll do a quick little brief bit here. We're not going to go super deep into any of that. But we need to know what IP addresses are. We need to know what port numbers are. We need to know what TCP and UDP are in order for us to do sockets, these sorts of things. So just a basic level here, not too much trouble here, right? We're going to use asynchronous socket channels, and we'll go through their example and see how that all works. So an IP address is your internet protocol address here. This is how you are identified on your network. So if you open up your terminal here, and you type ipconfig eventually. Sorry, mine's a little slow. Sorry. Ipconfig. It tells you all the things about all of your connections here. Now, you might have more than one, right? You might have a Ethernet, a physical adapter. It's not connected, right? I didn't plug in. Mine's my wireless adapter here. There's some other stuff. Don't worry too much about it here, but here's my wireless adapter for me. So this is the information about my connection currently here, right? So the interesting one here is your IPv4 address. You also have an IPv6. This is becoming more and more common. This one is all in hex and it's longer. This one is done in numbers that are 8-bit. They're 0 to 255. So you have 4 numbers from 0 to 255 here that make up your address. So 4 bytes, right? Make up your network address here. So 141, 215, 203.78. So that is my computer's network address on the wireless network here. So someone else with a different computer can go and connect to mine using this IP address. It's my name, essentially. It's my location, right? You have an address for your house. You have a network address for your computer, where it is currently. Now, your physical house address doesn't change because your house doesn't move, but laptops move, right? So you'll have an IP address when you're here on the network. You'll have an IP address when you're at Starbucks. You'll have an IP address when you're at home. You'll have an IP address at the library. That can change, right? It's what you're currently connected to, right? And that's okay. So that's our current connection. So um, you can use things like names for things instead of using IP addresses here. That is what we'll call DNS. So DNS, nope, sorry, I was going to do a new tab here. DNS is our domain name system here. This links names to IP addresses. So no one wants to memorize an IP address, they want to know a name. So if I want to go to google.com here, I use DNS here. Behind the scenes, it all happens automatically for us because our browser is really cool. It says, hey, what IP address is www.google.com? And then we go get it. So we can go look it up here. Just look up, google.com. Does that one work? So google.com looks like it is 142, 250, 191, 174 currently. And Google actually has lots of IP addresses. It's okay, right? And not too big of a deal. So we can use names. We're not going to bother with any of that name stuff because that's harder to do on local small networks here. Right? The idea with domain names and DNS is that this is a public IP address somewhere that you want the entire public to get to. Very cool, very exciting. We like that. People want to go out and find Google. Google wants people to go out and find them. Right? They don't make money if people don't go to google.com and search. Right? So they want to be found. So for our purpose, we're not going to use any of the names. We're just going to use the IP address. So every time we make a new connection, we might get a new IP address. Generally, they stay pretty much the same. There's some cool stuff behind the scenes that like remembers your computer and remembers your IP address and it will save it for you and other fancy things that networking is cool for. Um, but it could change. But so for now, I'll have this address. This will be the address of my computer here. And on my computer, if I'm running a web server here, actually I've got XAMPP currently for a different thing. I can go get at my web server here. I'm running Apache at the moment here. So I can put in my IP address here and it goes to my computer because this is my address here and the web server is hosting this page here. This is a built-in XAMPP is pretty cool. You get a database, you get PHP, excuse me, you get MySQL or MariaDB, sorry. It's technically not MySQL now that Oracle owns them because sure, whatever that happened to be. So you can get at my web server here. Now, this works because Apache is doing sorts of cool things behind the scenes and responding when it's get a web request. And it has these things called ports. So ports are specific sub pieces of that address. So imagine your address, your home address, and if you had 50 different spots here, you might have 50 different ports. Here's port 1, here's port 2, port 3, port 4, port 5, whatever it is here, right? Maybe it's like a room in your house or something. That's the port number. There are certain port numbers that are reserved for specific things. So port 80 is the default internet HTTP traffic port, right? If you connect on HTTPS, here the secure connection, you're using port 443. Not very interesting. You shouldn't memorize these things. They're not worth knowing. But we rely on well-known ports for well-known services. So when we write our own application, we're not going to use port 80. We're not going to use port 443. We're going to use some sort of custom port here that no one else is using. At least no one else on my computer is using, no one else on your computer is using. So there's a range of ports that are reserved as well-known ones, and then there's the rest of them here. There's somewhere around 65,000, if I recall, ports available. The first couple thousand are reserved. I forget exactly. We can Google it here. Range of reserved ports and unassigned ports. Let's see. Okay, so only the first 1,023. Okay, so a little slightly less than I thought of the well-known ports here. And then up to 49,000 are registered. And then dynamic here, private ports, 49,000 to 65,000 here. So we can use lots of interesting ports for different things here. Okay, so what we're going to do is our server will run and will listen on a specific port. So your server says, okay, I'm telling the operating system I want to listen up for this port here. And then if some traffic comes in over the network to your computer's address to that port, your application will handle it. It will get routed to your application, and your application can do whatever it wants to do with it here. So if you want to see what stuff is running, netstat, I'm doing a bunch of things apparently on my computer here. I've got a bunch of connections to different addresses here. There's the local address and the foreign address. So I'm listening on port 80 right now with this process number. So the PID is your process ID. So whatever process 29636 is, if I go check out Task Manager, and I want to, it's one of these fields, right? Or here, I can search it, I think, 29636. Look at that, my Apache HTTP server is running process number this. Right? That's the one listening on port 80. That's how I was able to respond when I put a web request out to my IP address, right? Don't worry about the zeros. It's okay. 127.0.0.1 is your home address, your local address here. This is yourself here. They put it on t-shirts and things like that. It's really fun if you like networking jokes. There's no place like 127.0.0.1 instead of there's no place like home because it's your home address. Okay. Nerds are funny. We're funny people. We like to make inside jokes. And then here's my other IP address, right? This is the one I've registered with on the wireless network here. So this is one I'm known on. And I'm listening on 80 as well for these ones here. And then I've established connections to some other place here. So I started on port 80 and I connected out to them, right? That's the remote one here. There's a bunch of different ports here. It's a bunch of different things I was listening for. I don't even know what some of these things are. And we could go look up the processes if we cared. Sure. But eventually, when we run our Java program, Java will be one of these processes listening on some funky port up in this range here that's probably not already picked, right? Because we want to have that port established. All right, so we have ports we can use. Our IP address, don't need to know the different schemes, that's okay. Port numbers, how they're used, and then TCP and UDP are different methods of connection here. TCP is a relatively common method of connecting that relies on acknowledging your packets. So individual packets of data that go across the network. We chunk up a large network request into small pieces and send small piece at a time, small piece at a time, small piece at a time, small piece at a time. And then along the way, we make sure, hey, did you get that small piece here? And there's some cool process. There's like a checksum involved and some checking behind the scenes to make sure, yes, I got the packet and yes, I got all the information in that packet here. There's some cool stuff in networking. So TCP does the checking for us. We establish a connection here, and we make sure that every packet made it correctly. It's important that you get the right data. For most connections here, we like TCP. This one's pretty good. UDP is just sending with no receipts. All you're doing is you're shooting out the data, and you're hoping they catch it. This sort of thing is much more common for like streaming, right? I'm just going to stream the data out. I don't care if you miss a packet or two. You might just drop a frame. You might just have a little blip in your connection. It doesn't matter. I'm not going to go resend it because you don't want the delay of having to process and put them back in the right order and figure out which one you missed. You're just going to stream the data out here, and whoever's receiving it's going to play it the best that they can. If they miss something, they miss something. Right? It's not mission critical sort of stuff here. So in general, we want TCP connections if we want to ensure that the data actually made it here. And there's a funny joke about that. There's a joke about TCP and UDP. Did you get it? I think it's this one. Yeah. Do you want to hear a joke about TCP IP? So the TCP connection. So we're going to establish a connection and confirm it. Yes, I'd like to hear a joke. We've started here. Are you ready to hear the joke? Yes, I'm ready. So, okay, we've started our connection. Now, are you ready for me to send data? Here's a joke. Did you receive the joke? Yes, I received the joke. Excellent, you received the joke. So it's a very verbose protocol. A lot of stuff happening behind the scenes, right? You start your connection, you ask if they're ready, you send it, you make sure they got it, right? But again, if you want to make sure we get our data here and properly get the data if it matters, this is the good connection here. You want that stuff. So that's our funny joke. Now you get the joke and you can laugh about it or cry because now that you understand it, it's kind of sad. Whichever. All right. Excuse me. All right. URIs, URLs, and URNs. It's very semantic difference here. URLs, right? Our browsers are URLs. Right? All URLs are technically URIs, if I remember right, but not all URIs are URLs. Again, it doesn't matter too much here. It's just, oh wait, how do we name something here? Right? That's all. All right. So we're going to write our network application. We're focusing on local area networks here, not larger ones. It used to just be LANs and WANs. I don't know if any other people use these other terms here, but people have all sorts of acronyms here. But your local area network is your local network. That's your home network, right? The Starbucks network, whatever it is, just that essentially the one wireless router. Maybe a little bit more beyond that, but again, very small, right? We all connect to the same central location here, and that's great. Um, I guess some other pieces we didn't talk about. Oh, bummer. How network connections work. You have to go connect to a router that runs a gateway. So we all have a local connection, and then we all go out to our one gateway to the World Wide Web, to the rest of the internet here. And fancier network connections have more than one gateway and all sorts of other redundancies and fun stuff here. But essentially, my gateway, oh goodness, I lost it here, is this address here. So everything that I want to send to the internet goes to the gateway first, and the gateway then is responsible for routing it to the rest of the internet. A router takes your local traffic and gets it out to the internet, and then sometimes takes internet traffic and brings it back in, right? So that's the point of the gateway here. So we're not planning to do anything beyond routing. We don't need to go anywhere out into the rest of the wild world here. Uh, Getting data in is harder. Most routers just don't accept connections. So the only way that connections come in for a lot of local networks here is once you've sent a request out, the router's like, oh, you started a connection. Now I'll let stuff back in on that connection. But if you think about it, you don't want people on the internet coming and connecting to you 99% of the time, probably even 99.9999% of the time. You don't want some random people coming and connecting to your computer, right? You only want the internet when you go ask for it, right? This used to be a real big issue back before we realized people like to do bad things with computers and internets. Like the default was, yes, it was open, and you just plugged in a computer and put it on the internet, and you started getting internet traffic. And then we finally realized that's probably a bad thing. We shouldn't. I mean, finally, it was like 15 years ago we stopped doing that, and default routers and gateways now don't accept traffic. So the downside is if you want to play Minecraft with your friends and you want to run a Minecraft server, you have to specifically tell your router now, please let traffic in that I didn't ask for because I'm hosting a server. I want traffic to come in from the internet, and you'll tell it a specific port number most of the time. And like, hey, let traffic in on port 9275 because that's my Minecraft server's port or something like that here. We can do those sorts of connections. So if you've ever set up a Minecraft server on your local network, you have to find your port, connect to it, or hopefully it just showed up in the list, right? So that sort of stuff. Um, Opening out to the wide internet takes some more steps. And again, that's why we're not going to do that. It's just a lot more work, and we can't even do that on the campus network here. They're not going to let us open up ports. Right? It's just not going to happen. So it'll just be our local connection. So we have to be all in the same network so that we can go find each other by our network addresses here if we're all on the same network. So if I'm on my hotspots network and you're on the campus network, we can't talk to each other because there's the great wide internet between us, right? But if we're both on the campus wireless here, we should probably be able to see each other, right? Because we're both on the campus wireless network. Nothing has to go out to the internet here. All right. Um, Networks. The seven, oh my goodness, this isn't even 7 layers. What happened to that? They've simplified it. Okay, that's fine. When I learned it years and years and years ago, there were more layers here, but that's fine. So we have the application layer. This is what people deal with here. They want to know their application works. Behind the scenes, all this other stuff has to exist to facilitate your application working. You have to have some method of transport. How are we transporting the data back and forth? Is it HTTP? Is it just a regular TCP? Is it a UDP? Is it SSL traffic or SSH traffic? Right? How are we doing these sorts of things here? And then where's the internet layer here? where are we connecting to? So how do we transport it and what are we transporting it on? Here, the internet, and then your network interface. So if we actually physically plug in or your wireless router, or I'm sorry, your wireless card, your computers have a wireless network card that is the interface itself here. That's what it connects to. And then it has the actual physical piece that connects to your computer. Right. So all this stuff supports it down the suite, which is really cool. All right. And you can go through and read this chapter. It's only, how many pages is this chapter? 559 to 698. Oof. It's a thick book. I think that's why we don't use this one as the main book. This one's a little thick here. Um, so, um, yeah, how all this stuff works. Great. So from my application to the receiver's application, right, all this sort of connection stuff happens behind the scenes, which is fun. Um, your IP address here, great numbers. Um, IPv6 is 128-bit versus 32-bit. So now we can fit more things, right? We ran out of IP addresses a long time ago. So we had to move to a bigger addressing scheme. This is all hexadecimal based and longer, and that's fun. Um, and you can send more at a time, which is nice. The special IP addresses, there's some fancy ones here. Don't worry too much about it. Um, Port numbers, right? The where we're sending it to, right? From 0 to 65,000 or some here. I bet that's a number power of 2 minus 1 is my guess here. Just, but we'll see. Yeah, DNS, how that all works here. Works. Okay. How our Java stuff works. So all of that was preface to writing a Java application. So there's a bunch of background stuff we have to have before we get to it that we know how that all works. So our connections we'll call sockets here. So we use sockets to communicate over specific ports with a client and server. So a client connects out to the server responds to the client. Right? That's how these connections sort of work here. There is a way of connecting that is just client client here. If any of you are old enough to remember the application called Skype here, that was designed initially as a client to client communication tool. So when you made a Skype call, you connected directly to the other person. And then Microsoft bought it and, in their wisdom, decided they were going to shift to a client and server paradigm so that everybody connects to Microsoft. And then Microsoft takes your call and routes it between the two people. So you didn't connect directly. There was some benefit to it here, and people who like conspiracy theories think Microsoft wanted to listen in on everything, and um, who knows exactly? Somebody does, I'm sure, but just a different way of connecting. So again, we're going to follow the client server paradigm where there's a central server process, not a client to client communication here. Uh, that sort of thing. So is BitTorrent still a thing, or torrenting still a thing? Not really. That was another client to client. So you would register yourself as a node and say, hey, I've got some data I can share. And then another person could connect right to you and get that data here. So we could distribute things, definitely not stolen MP3s or anything like that. Definitely didn't do that over BitTorrent at all. Um, it was just a good way to share data, right?
Yeah.
I'm sorry?
Why did Zoom kind of boom during COVID and not like Skype?
You know, I think that's a marketing answer there for why Zoom became so popular. Like it was just at the right place at the right time, and they offered a free service for it here, and it was they had, for COVID, they actually were with a couple schools. Like they pitched it as a nice tool for schools to use as a friendly, quick, easy download. There were other tools. WebEx was a tool that was used. I think Cisco owned it, or somebody owned WebEx was another tool. Um, we used to have one called Blue Jeans. I don't know why. Probably someone wrote it locally. We like the color blue here. Um, yeah, there were a lot of different tools, but Skype happened to be at the right time, or I'm sorry, Zoom happened to be at the right time, was offering, hey, 45 minutes for free to make an account. So it got some quick adoption really fast. Was a pretty quick install. You could explain it to grandma. Hey, grandma, just go to the website, zoom.com, and go download it. For some reason, that was easier for people than WebEx. Like WebEx had all sorts of rules around registering and signing in. It was a small pain to get up and running here. Um, yeah, so I think it was just the right place at the right time for Zoom. Yeah, it was weird. It was like global phenomenon, right? Like everyone was on Zoom, it seemed like. All right, so our socket here is a connection-oriented socket. So we want a connection-oriented socket. We're going to stream data here to keep that stream live, or you want to have a datagram, your connectionless socket here. Um, so with TCP, right, that's the one that makes sure we have the actual connection here, make sure all the data is ordered correctly, the pieces of it here, as we break a large piece of information into smaller packets to send over the network. There's certain sizes we want to get to because they found people who study this sort of things that that's the optimal size so that you can send enough data without all the overhead, but you're also not sending too much that if you lose one, it gets to be a big deal here. Let's see. Circuit sockets, connections. Um, yeah, it's their overhead. So every time we send a piece of information with TCP, it has to send, hey, this is the packet number, this is the sequence number, here's the this sort of thing, all the confirmation that has to happen. It's a little bit extra. UDP is the connection list. It's just shooting it out. They're probably getting it here, but it's not as reliable. All right, so we go and do a bunch of stuff. Oh my goodness. Java net packages, JavaX net packages. Excuse me, you might have your INET address, your internet address here for IPv4, IPv6, which is easy, depending which one you want to use. You can get by names here. So we've got some cool stuff built in that will go and find IP addresses, network connections for you by names versus other things here. Your local host address here. We can go and get, hey, what is my computer's local host here? But any of this stuff here is likely to break. So we all use try blocks here because networks, funky things will happen all the time here. So let me do another package or another project here for networking. Networking. If I can spell it right here, that would be useful. And we'll see if we can get their quick little starter code. I don't want this garbage. You can change this template so you don't get the garbage here. Oops, too much. All right. Paste in that one here. Anyway, I'm going to go import INET address, import JavaNet. Why is it not like that? Oh, you could do better with your logging. Thanks. That's a great suggestion here. Very exciting. So my computer's name is Victus, yay branding here, and my computer's IP address here. So I get the host address here versus host name, right? So your computer's name, I think that's in the system properties. Properties. It's been a little while here. Computer name, yeah, there it is set, at least in Windows land, you can set your computer name here. Um, it's possible we both have computers with the same name here. So again, the address is much more specific here than the name. If your last name was Smith and you lived on Main Street and someone just sent a letter to Smith on Main Street and didn't include your house number, it probably didn't get to you, right? So name we know is a little bit flawed here. So the address is much more specific there. All right, so we got our name, we got our address here. Very cool. Then you can go and use these sorts of things, do all the lookups, get all your details here, other fun things. To represent a socket, then, it's a particular address and a specific port, right? So that'll be your host name and the specific port we're listening on here. So if we want to make our socket address here, like, hey, this is, so ::1 is the same as the 127.0.0.1, but this is IPv6 here. So this is yourself here at a particular address here. So let's go steal their address and see if it, or steal their code here. See if this one works for us. We should cite our source. I should cite. I don't know why I keep saying I'm we here. So we'll make sure we're writing down where we get all this from here. Um, I guess we could just comment this one. Oh, it was already main. That's why. Sorry. Main. And too many of those then. Oops. Just one. All right. So INET socket address. Yeah, import that one, please. Great. Okay. We should be up and running here. And let me add my citation before I forget. It's stolen from, or Apple, whatever you want to call it here. All right, so we can see, hey, here's my socket address, right? This colon, the IPv6 version here, one on a specific port, right, which is cool. So now we can see I've got a specific port. Okay. Create my server socket, TCP server socket is the server socket class. Quote, localhost is my local computer. This is another, there's 127.0.0.1, there's localhost. There's actually a file that maps this, which is messy to change, but that's fine here. And then you will bind it to say, okay, I want to hold on to that port and create a connection here, right? And keep it. So that's doing the binding here with it. You don't need to go listen, right? Because we're doing our binding. Okay, so we'll make our server socket with our address here, 100-way queue size for this particular port. So we're going to pick a large port number here above the reserve section here that no one else is using. If that port's in use, it's going to crash on us here. And it just sits and waits for connections here, which is cool. So we can sit and wait for someone to connect out to our socket. Right? Then you can read data off the socket with a buffered reader. Right? We did the file reading with like a buffered reader and a file reader, these sorts of things. So buffered reader can work off of that here, off of the socket here, and we can go and get data from that connection. So in this one, we'll write the data to the buffer, and then we flush the buffer, right? This is our buffered writer here, and we're going to send it to the socket. So once we close it, you have to create a brand new one. So it like completely kills it here once you call close. The other thing you can do is you can use a while true loop, which seems a little bit silly, but essentially we're just running and we're accepting data. I don't want this to stop. I just want it to sit here and accept data, right? Because I want to sit and listen as a network server. I don't want it to take one piece of data in and then quit. It's not very helpful to be a network server here. So we want to stay open here. Now, the only downside with this is it handles one at a time. Right? I will handle that connection here one at a time. So if you don't have a whole lot of connections and it doesn't take you much time here, I can quickly handle this sort of thing. It doesn't need to be asynchronous at this point. It's one response in, I do a quick thing, I send it back out. That's a nice, easy way to do it here. But the next piece is we create separate threads so we can have multiple pieces. And that's why we had to talk about threading first. So what we're going to do is we're going to, while true, exist here. We're going to just run, and then we're going to accept connections. And what we're going to do is we're going to make a runnable here, right, that uses that thread runnable interface. And this is what happens when we go and get a connection here. And then we can go and start that thread. So every time we get a connection, we push it off on a new thread. Right? We're just going to sit and wait. We're accepting a connection. Here's a runnable. Let's go start as soon as I get my connection. I'm just going to sit and wait. Once I get some data in, let's hand it off to the thread. So this, every time it gets a new request in, will shoot off a new thread. This is really nice. Now, the downside to this is you've got too many. So if you get 1,000 requests in all at once, your computer probably can't handle 1,000 threads doing a whole bunch of interesting stuff all at once, right? 2 or 3, 4, 5, 10, 15, that should be fine, right? For our level here with a team of 3 or 4 people, you can handle 4 clients. Easy, right? Not going to be any trouble here. So that'll be fine for you here. So this example then makes our server socket, right, stays in the loop here to connect, right? And it just says, okay, let's go handle that connection. So what are we going to do when we handle it? Okay, well, here's a buffer reader, right? Let's go get some data. We got some data from the client. Let's just write it. We're not doing anything really interesting here. We're just going to spit out what I got, right? A little demo of it here. Okay, so we go through and we'll steal this one, right? It's my echo server. It's just going to respond with whatever data we get here. I guess we probably don't need any of this one here. Let's drop it all in. And I'll just call this one main. And oops, we're not this package. I forgot. Okay. So it goes and makes a server socket. It's just going to listen for connections. When it gets some data, it will go and write that data. So it's waiting for the connection on 12,900. Okay. So this Java process is just going to sit and run and wait. I don't have a client yet that's connecting to it. Right? So I need to go make the client piece that goes and connects to this one here. Right? So I'm going to make a socket, right, that connects to right? Whatever other address here I want, and goes and finds that port number and connects to it. So this one echoes the client application, this listing here, right? This is my client side. So this is 1290, right? We're going to use that socket on 1290 here. Um, here's the client side. Is that the same? Is that the one I just wrote? Did I jump back up? It is. Shoot. Oh no, there it is. Echo client. The other one was the server, right? Echo server. Yeah, Echo server. Okay, so here's the client. So we got to go do another one here. Let's go grab this one, and I need to go make another instance here. Right, so I'm going to make another new project here. Let's call this the Echo client. I want to do a new window because I want to leave this one running. So this is where it gets a little interesting, or one of you could run probably from your computer if you wanted. Here, go connect into mine. Let's go with me again here. Um, so now we're going to go and connect here. When this one runs, it says, okay, started a client here, local. Now this one is a different port because I want to connect into the other one, right, on 12,900 or whatever here. So what's the message I want to send? So what should we send? Should we send hello world?
Testing.
Testing. The server echoes back testing. So we see on the server side, it said, hey, received a connection from here. We got the message testing. So because this is running and everyone is going to start a new thread, I can have a bunch of these clients all connected at the same time. And if I'm like, my message is the entire book of Moby Dick, and I have to process it here, it's going to happen on its own thread. It's not going to be sitting, waiting, blocking another client from connecting. Right. So this is not a full-on chat server. It's not interesting like Discord or anything yet. This is one client connecting to one server here. So we have to figure out the next pieces. How do we expand on this to get, okay, I want to connect in. How do I know where am I storing that information? So the server needs to have where that stored information is here, probably in a database, right? You could use a local file. I didn't require everyone to use a database. And you probably want a database to store your information. If you just want to use a local file, it's fine. You can still get the points for the project here, but ideally you've used a database because that again will show you can do more with your development work if you want this as some sort of portfolio project. Hey, I'm getting data in, I'm storing my database, right? All the chat information in Discord is stored in the database somewhere. I think they use MongoDB actually as a document database because I don't think it's like a traditional transactional one, but I don't know. Can we Google it? Does Discord store in a database? I don't know if that's the right question to ask or not here. Uh, from MongoDB to Cassandra and then Scala DB? Interesting. 177 nodes in 2022 down to 72. They went from 7 down to 72. Wow, reduce the number of nodes. Anyway, so they show some cool stuff on how they do some other things, which is really cool. Like you can go through and look at their blog, right? Trillions of messages here, which is kind of cool that they publish this information. This is a fun piece here. People like to show off their fun tech stuff here. But anyway, that's beside the point. So running a client, running a server, right? It's not a one-to-one. They don't have a million server processes running, that sort of thing. But we're going to run separate Java applications. Now, if we look at our piece here again, so we go netstat-aon here. I want to find, hang on, I want to find string, nope, sorry. Find string 12900, right? So I can see, hey, process 17416 is listening and process 18572 has connected from this port to this port. Right? So I picked a port to send out on to connect into a different port, right? So that way it can send data back. So whatever port I use is how the data is coming back in on that. So if we were connecting out to the internet, now my router knows, hey, data can come back on port 52322 for Eric's computer because they asked for it. I'm going to leave that open and allow data to come back and forth with that connection here. So if I can look up those two Java processes here, 17.416, right? 17.416 we'll see is Java, right? And then the same 18.572 is also Java. Right? One's the server, one's the client. Okay. Does that part make sense? So I can stop those here and we'll stop out our connections. Right. I think that's probably as far as I need to get tonight. I think we've already lost a couple of people. It's been a bit of a long night here. So this sets the stage for what we're going to do. So next week, hopefully, we can finish out our little basic client server chat app here. We're not going to be quite as fancy as Discord with like lots of different servers, but I might have, hey, here's one chat room, here's another chat room. And then I can load up, here's your chat history, essentially. And you can send a chat in and we'll save that. I think that's the plan for next week. Does that sound good? And then the week after that is Thanksgiving week. So we're off after that. And then the week after that here is project work time. The plan is to just give your team time to meet on 12/4. So I won't see you from 11/20 until you present your final projects on the 11th is the plan. So I'll see you next week. I won't see you for Thanksgiving break. Have a good Thanksgiving. If you need a place to come eat some turkey, let me know. Um, we use a big hall for my extended family, my wife's extended family. And then final project work time, just get together with your team. Please don't let them say they're busy Thursday night because everyone signed up for this class not knowing it was flexible. Like lean on them really hard. Hey, you should have been free, or they've got some time here. Um, if you can finish by 12/4, that's fantastic. Oh, I forgot to give you the requirements here as well for projects. Sorry. I talked about it. I didn't put it in here for anyone who doesn't watch the videos here. Um, Teams must have a minimum 10 Git commits across 10 separate days, showing incremental progress of working applications. Add screenshots of what is running each commit to the README. So we're going to use this README as sort of a log. Hey, here's what's going today. It should run. It's okay if you got stuck somewhere where nothing run. Like, okay, today didn't work, but most of our commits should have something working. Okay, hey, I started on the server class. Hey, I started on some business logic here. Hey, I started on this application. Hey, I have the UI starts, right? Little small pieces at a time here to encourage you with this one here. So projects without at least 10 commits over 10 days will not be scored. Hopefully people see that one here. And I think you want a score on the final project because if you don't get a score on the final project, again, you fail the class. It's intentional. Right? Everything we've done sort of builds up into this. And ideally, it's a fun little portfolio project, something you can show off and talk about here. When you get into interviews, no one cares if you can do the traveling salesman algorithm. Literally everyone who's done a computer science degree has done the traveling salesman algorithm. It's not interesting. I don't want to hear it. Right? What I want to hear about is the cool stuff you did that you learned from. So we interviewed people. We talk about what was a fun project you did. What did you learn about it here? What was hard about it? How did you go find that information when you got stuck? These sorts of things. And that's one of the reasons we have our capstone class. You take senior design 1 and 2 to do a 8-month long major project. That's like a 1,000-hour project, right? That's something you can put on your portfolio, talk about. You've used mostly a real world experience. It's not exactly a still school, but a way of doing that. So will help you build out your portfolio. Okay. All right. Let me stop recording.